Well, welcome back, everyone, to our celebration activities. Today, we have, in fact, a double celebration as in addition to the 60th birthday anniversary of our mathematics department, this month we are celebrating the centennial of the birth of Jose Adem. Jose is one of the two central figures in the founding of our department back in 1961. His mathematical legacy is simply ubiquitous in algebraic topology, as the Adem relations describe one of the central structures associated to the cohomology of general spaces. And continuing with these high standards, our speaker today is a world-leading mathematician who has made important qualitative and calculational contributions in group cohomology and its applications to algebraic topology. He has been managing editor of the memoirs and of the transactions of the AMS. He is a fellow of both the Canadian and American Mathematical Societies and has won several prizes, most recently the Jeffrey Williams Prize, granted by the Canadian Mathematical Society in recognition of outstanding contributions to mathematical research. Our speaker has also worked in narrowing the gap between mathematical sciences and applications. He has been director of the Pacific Institute for the Mathematical Sciences, as well as chief executive officer and scientific director of MITAX, an organization fostering collaboration between industry, academics, and government in Canada. Currently, he is president of the Natural Sciences and Engineering Research Council of that country and has just been elected member of the Royal Society of Canada. It is thus my great pleasure to deeply thank Professor Alejandro Adem for kindly accepting to take part in our celebration activities by sharing with us his insights on minimal Euler characteristics for even-dimensional manifolds with finite fundamental group. Please, Alejandro.
Thank you, Jesus, for that introduction. It's a real pleasure and honor for me to be here, celebrating the 60th anniversary of the Simvestav and also the 100th anniversary of the birth of Jose Adem. For me, the Simvestav was very important for my career. I remember the events that were organized there, you, Jesus, and your colleagues, and of course, Samuel Gittler, who played such an important role. And I was just recalling that the first event that I attended as a mathematician was my uncle Jose's 60th birthday, which was held in Huastepec in Mexico. And that's where I met all the wonderful topologists who came there. And that's when I decided that I also wanted to be a topologist. I know the Simvestav has had a huge impact on mathematics in Mexico, in Latin America, in fact, worldwide. So I celebrate and congratulate you and all your colleagues on this wonderful anniversary. Now, let me now share the screen to start my lecture here. Hopefully you can all see this. Yes? Good. So I'm going to be talking a bit about group actions today and how you can say things about the existence of group actions working from Euler characteristics. So recognizing that everyone is not an expert, I decided to make this fairly expository talk. And you can always look up the details in the papers which are posted on my website or in the archive. So, okay. So let me start out by giving you the framework. So we're going to let X denote what I call a nice topological space. So for the purposes of this talk, we could very well be looking at a compact manifold. And the philosophy here is that to understand an object One approach is to study the group of symmetries. So what are the symmetries of a topological space? So we think of a group G as realized as a group of symmetries for a space X if you have a homomorphism from G to the homeomorphisms of X. And the term on the right denotes the group of homeomorphisms from X to X. So continuous invertible functions with a continuous inverse. So you can think of this as an action of G on the topological space X. And the action will be effective if this map is an injection. So if you can fully embed G, think of G as a subgroup of the homeomorphisms of X. This, of course, still gives us a lot of possibilities. Mathematicians have ways of understanding the different possibilities, finding some kind of way of measuring what these actions look like, and then breaking them apart into pieces so that we can understand them locally and then globally. So to be more precise, there's associated to a point in a space X with a group action, we can define its isotropy subgroup as a set of elements in G which fix X. So this space G sub X is a subgroup of G. So associated to a group action, we have a collection of subgroups at every point in the space X. So that's important because it's telling us that from the group action, you have a collection of subgroups. In fact, more technically, a family of subgroups, the isotropy family of subgroups. Now, conversely, if I have a subgroup H of G, we can define its fixed point set, the elements X in X, so the elements in the space, which are fixed by all elements in the subgroup H. So this is the fixed points under H. So now, associated to a group action, we have this collection of subspaces, the fixed point sets under all the subgroups. And what we know is that to properly understand an action of a group, and here I am, by and large, would like to focus on finite groups, but you can do this analysis for any group, but we know a lot more about the situation for finite or compact groups. You have to understand all the isotropy subgroups. You have to understand all the fixed point sets simultaneously and how they interact. So you can see, give you some idea as to the magnitude of the problem. And here you see here that the relationship between the subgroup lattice and the fixed point sets. So now in this talk, we're going to be specialized into a very special situation, which arises very naturally and which connects this theory to homotopy theory and the theory of covering spaces. Okay, get this to work. So I want to focus here on the situation, the special case of free actions. So let's recall what that means. An action of G on X is said to be free if the isotropy is trivial at every point X in X. Or equivalently, if the fixed point sets X upper H are the empty set for all non-trivial subgroups H in G. So this is a very special kind of action. It's an action where the group is moving the elements and it gives you a complete orbit. So an element with the action of the G gives you a complete orbit, and you recover as many elements in the orbit as the order of the group in the case of a finite group action. And we will be by and large focusing on free actions. And because there are very nice things that you can say about the orbit spaces of a free action. So if I take a free action of G on X, we can take, in fact, any action, we can take the space of orbits with the quotient topology. So we identify two elements if they can be taken by elements in the group under the action. Now the map, the natural quotient map from x of x to x mod g is a covering if the action is free. And the way you see that is a small neighborhood in x mod g lifts to as many copies as the order of g, little neighborhoods, each of them mapping homeomorphically to x mod g. So that is a covering. I'm describing the case of a finite group. More generally, you would want to have a principal bundle, but okay, locally trivial. And if M is a manifold, then M mod G will once again be a manifold. Oh, sorry. That's because, again, a little neighborhood in M mod G lifts to a neighborhood in M, to a collection of neighborhoods up there. And if M is locally Euclidean, then clearly M mod G will also be locally Euclidean. Now, if you stare at this very hard, and you start cutting things up into little pieces, and if you like Euler characteristics and combinatorial topology, then you can see that there's a nice formula for Euler characteristics. The Euler characteristic of the space upstairs is equal to the order of the group times the Euler characteristic of the quotient. And that's because if you have, say, a triangle downstairs, if it's a sufficiently small triangle, you'll have as many triangles upstairs in the pre-image as the order of the group. So you can work out the arithmetic and you get this formula. Now, in the case of an action which is not free, then of course this orbit space still exists. It's extremely interesting. Now, the object we would get in that case would be something like an orbifold in the case of a finite group action. Theory of orbifolds, again, is a very interesting subject, but technically that study is a little bit different in the case of free actions. And again, the point here about free actions is that this study connects to both the homotopy theory and to the cohomology of groups, representation theory and cohomology of groups, as we will see. So here's an example, a surface of genus 4. We have a free Z mod 3 action. Of course, just spinning on this axis, you get a free Z mod 3 action. So that gives you an opportunity to visualize what an action is. So they can be very beautiful, very natural. In fact, drawing pictures of free group actions on surfaces is a lot of fun. I encourage every elementary school kid to do that. And in fact, I have a theory about teaching topology to children in elementary school. I think a lot of what we know in topology could be taught to kids in elementary school. Okay, so that's a beautiful example. Here's another example. The Euler characteristic is equal to, so in this example here, the Euler characteristic is equal to -6. So if we divide out by the Z mod 3 symmetry, we obtain a surface of Euler characteristic equal to -2, which must therefore be a surface of genus equal to 2. So here what we're saying is, well, if you have a surface compact, in fact, a Riemann surface, and you divide out by the action of a finite group that preserves orientation. In this case, that's automatic because the group has odd order. So it doesn't do strange things, so that the quotient does not have any Mobius strips. And then you obtain another Riemann surface, compact Riemann surface in the quotient, and you can figure out what its Euler characteristic is from that formula I showed you. So this is a very nice situation then when you have a positive Euler characteristic and a finite group acting freely. Then given the classification theorem of surfaces, you can write down the answer completely. So now you can reach the following problem out of this. Given the closed manifold M, describe all finite groups that can act freely on it. That's an interesting question, which I leave to the, somebody can do this as homework maybe. So it's a problem that kind of underlies a lot of the work that you see over many years and in many different contexts. And it's a kind of problem which is so general that it needs to have some prescription. What manifold are you talking about? What kind of finite groups are you talking about? But it is a very interesting, motivating question. Now, for example, if you have something of Euler characteristic 1, something which is contractible, then of course the only trivial group that can act freely is only group that can act, finite group that can act freely on this disk is going to be the trivial group. So that's a very simple one. Now, what about even dimensional spheres? If you have an even dimensional sphere, its Euler characteristic is equal to 2. You can compute that just from a decomposition of the sphere. And therefore, if G acts freely on such a space M, then either G is trivial or Z mod 2. And the example you have is the antipodal action. So here we're in very good shape. So you might think we'll make some progress on this problem. But what if the Euler characteristic is equal to 0? So then our divisibility condition is not saying very much. So what about free finite group actions on an odd dimensional sphere? So this was the big motivating question in this subject for many years, trying to understand free finite group actions on odd dimensional spheres. So that turned out to be quite a challenge. And let me just review a bit the results there, because it kind of connects the theory to cohomology and to homotopy theory, which we had promised. So there's the theorem from Smith, 1940. If a finite group G acts freely on a sphere, then all of its abelian subgroups are cyclic. And that means is that G does not contain any subgroup of the form ZP cross ZP for P a prime. So this was at the time, I think a fairly a remarkable theorem, because it was telling you that a geometric condition on an action, in other words, an action on a particular space, was implying a group theoretic condition. It's telling us that the group has this particular property of not containing ZP cross ZP as a subgroup. So then you have to say, well, group actions are giving us conditions on the group. What kind of a condition is this condition? And that's of course the start of a whole theory. So examples: the cyclic group acts freely on any odd dimensional sphere. You can start with action on a circle as a subgroup, and then by taking joins, you can construct free actions on odd dimensional spheres. Slightly more interesting example is the quaternion group of order 8, which is classically known to be a subgroup of SU2. SU2 is isomorphic or homeomorphic to the 3-sphere, so it acts freely on it. That's the classical action of the quaternion group on the 3-sphere. So those are the examples that are very easy to come by. And notice that these groups do not contain ZP cross ZP as a subgroup. And there's a theorem then by Milner that said the following: a finite group G acting freely on a sphere must have every element of order 2 in its center. Now, what does that mean exactly? That means that every element of order 2, so every element whose square is equal to 1, has to commute with every other element in the group. So that's a very beautiful condition on a group. And to make this more concrete, this means, for example, that the dihedral groups of order 2p cannot act freely on any sphere. This group, order 2p, this you can get from taking an action of Z mod 2 on Z mod p through the natural action of Z mod 2 on Z mod p as an automorphism. And you can construct that a semi-direct product. That's how you get D2P. And this very simple group cannot act freely on any sphere. So it turns out, however, that that's a geometric condition. And this is where geometry and homotopy theory separate. And here this is a theorem of Swann's, which said the following: G acts freely on a finite complex X homotopy equivalent to a sphere, to some sphere for n bigger than 0, if and only if every abelian subgroup in G is cyclic. So the condition obtained by Smith, in fact, guarantees that you have a free action on a homotopy sphere. So how should non-experts think of it? Well, a sphere is somehow rigid, geometric condition of an action, actual action on a sphere, Milner tells us you have this rigidity and that manifests itself by that group theoretic condition. Swans tells us, well, if you loosen that up, if you do spaces up to homotopy, then really Smith's condition is necessary and sufficient. And of course, Smith's condition, you can think of it from the point of view of homological algebra, and it is the condition precisely that the group have periodic cohomology. I don't think we're going to talk about periodic cohomology because this is supposed to be a non-technical talk, but this is a notion of an invariant which can be associated to groups, in particular for finite groups, and periodicity tells you that you have a repetition. You compute through a range and then things repeat themselves. And that's a very beautiful homological condition, but it's equivalent to this very simple group theoretic condition. So then, this is telling us then that to get the big answer, you're going to have to do a considerable amount of geometric work. So that's where our friends who work in surgery theory came in. There's a lot of work in developing the geometric aspects of group actions. And so just to close up, so this dihedral group will act on a homotopy sphere. So just to make that clear. But now what is the big geometric result? Well, a characterization of all finite groups that act freely and smoothly on some sphere. Precisely, these are the groups, the finite groups that act freely and smoothly on some n-dimensional sphere. These are happens if and only if all the abelian subgroups in G are cyclic and every involution is central. So given a group of those conditions, we're not telling you what sphere they're acting on. We know there will be some sphere on which they will act freely and smoothly. So this is the solution of the spherical space form problem, which was very satisfying to individuals at that time. And as I mentioned before, it's a combination of group cohomology, homotopy theory, and surgery theory, because it's also geometric. Now, trying to go beyond these results has required using different technology from those areas, homotopy theory, representation theory, bundle theory, and group cohomology. So we're going to say a little bit about more recent developments. We're going to keep on pushing until we get to 2021. But the thing about mathematics is that the history gets longer and longer, right? So okay, so a theorem, let me state here a theorem that I proved with Jeff Smith, I guess already 2001, 20 years ago, amazing. So if a finite group G acts on a compact manifold M such that the isotropy subgroups do not contain any subgroup isomorphic to ZP cross ZP, then G acts freely on a space X, homotopy equivalent to the n sphere across M for some sufficiently large n. So, so this is sort of the condition on the isotropy. Before our condition was that the isotropy be trivial, and then we had a sphere, and then we saw that it had to satisfy this condition given by Smith, the condition that implies periodicity in the cohomology. Now we're requiring that condition on the isotropy subgroups. So what if you have an action where the isotropy is satisfies this periodic property? What can you say about the group, about the action? And it turns out that you can construct actions then on spheres cross M. So if you have this M which satisfies that condition on its isotropy, then you can construct this free action provided there's a product with a sphere. So it's kind of a situation where you can take care of the periodicity phenomena using fibrations, spherical fibrations. So there's a homotopy technique behind this. And the more general notion of topological spaces with periodic cohomology, this can be extended beyond group cohomology, so a very general notion. And what we provided, in fact, was a characterization of topological spaces with periodic cohomology. And this is a corollary of that more general result. I should say that the more general theory would be to try to understand spaces that have not periodic cohomology, but cohomology, which is has certain, if you want, cruel dimension, or are free and finitely generated over some polynomial subalgebra. So there's sort of commutative algebra conditions that should be reflected in geometric actions. So that's a very kind of vague and open question for people to think about. Now here's a very concrete problem, a very concrete application of these results now using some representation theory. So you have a prime bigger than 3, a finite P group acts freely and smoothly on some product of 2 spheres, if and only if P does not contain a copy of ZP cross ZP cross ZP. And I believe this is a result with Jim Davis and Ozgun Unlu. I believe this has been generalized in some directions. But this gives you an indication that if you want to construct actions on a product of 2 spheres, there'll be work to be done. So the theorem tells you that if you construct an action with periodic isotropy, then you'll have a free action on a product of 2 spheres. So if you construct an action on a sphere with periodic isotropy, you'll have a free action on a product of 2 spheres. And the second theorem is a geometric manifestation of that, constructed using, in fact, Stiefel manifolds. And I'll state here at the bottom, determining those finite groups that can act freely on a product of 2 spheres is an open problem. So again, homework for someone to work on. There's a nice, very interesting group that we know cannot appear if a group acts freely on a product of 2 spheres. There's some very interesting, more involved group theoretic condition that comes out of the analysis. And anyway, that's kind of where that lies. So now I want to switch gears in this little sort of survey and now consider a slightly different situation. Now let's consider the case of rational homology spheres. So we'll say that a closed 3-dimensional manifold is a rational homology sphere if it has the rational homology of the 3 sphere. So we just want to compute its homology with rational coefficients and show that it has the same homology as a 3 sphere. Now what this means for the uninitiated is that the abelianization of the fundamental group of M is a torsion module. That's what it means. And if you have a group action on the rational homology sphere, then this has a twisted ZG module structure. So so you'll have then this 3-manifold. This thing at the bottom, H1 of M, will be some torsion module. You cannot see this rationally, and it'll have some twisting under the action of G. Now you can show that every finite group acts freely on some rational homology 3 sphere. It's and the point here is that that torsion module can support action of any finite group. You can concoct things so that they it acts freely. So and of course the ones we care most about are actions that are untwisted. In other words, with a trivial action in homology. So when you work in topology and you have modules occurring in homology which are twisted, many times classical topologists don't like that. And you always wonder if you impose a condition of being untwisted, trivial action in homology, which is easier to visualize geometrically, where does that give us? So, so here's a result, a theorem joined with Ian Hambleton from 2019. So suppose now that G is a finite group acting freely and homologically trivially on the rational homology 3 sphere. Okay, so this is a space which has the rational homology of a 3 sphere. And so the data we have is, we have this module, H1 M, which is a finite group, finite abelian group. And now we're saying that this is untwisted. So it's just a finite abelian group with no real twisting by the group G. Now let S denote the product of precisely those primes which divide both the order of the group and the order of the first homology of M with Z coefficients, which is the same, as I said, as the abelianization of the fundamental group of M. Then there exists an extension. So we have a short exact sequence in the category of groups. So H is the kernel. This maps onto G. And we have this group in the middle, QS. Now H is, sorry about that. H is the component at all primes, the sum of the components at all primes that divide S. Right? So we're just taking those components, you know, this decomposition of an abelian group into its P primary components. I believe that's still taught in group theory courses. And where this is a central cyclic subgroup, and QS is a group such that all of its abelian subgroups are cyclic. And here, of course, we mean G. G is a group such that all of its abelian subgroups are cyclic. Sorry for the typo. So G is a group like the one we had said before, and it has all of its abelian subgroups are cyclic, and H is a central cyclic subgroup. So that's a description of the actions on rational homology spheres. So the best you can say is that the group G yes, okay. No, that was QS. No, that's right. Sorry, I got my typo right. It wasn't a typo. You have QS. G is the group that's acting, and you have that thing there. Oh, sorry about that. So that's correct. Okay. And QS is a group such as all its abelian subgroups are cyclic. And this is a central cyclic subgroup. So the canonical example you should think about is, for example, the 3-sphere has an action of the quaternion group of order 8. Now, if I divide out by the central cyclic subgroup of order 2, then I get an action on RP3, and it's an action of Z3 cross Z3, Z2 cross Z2. So there's a Z2 cross Z2 action on RP3. In this case, H would be Z mod 2, and G would be Z2 cross Z2. So Z2 cross Z2 acts freely on the rational homology 3-sphere, which is RP3. Okay, so the statement is correct. So it's kind of interesting because this has to be, you know, there's a cohomological analysis, and there's also input from what we know about periodic groups and things of that kind. So I put it out there as an example of the kinds of more intricate analysis that you need to do. Still in the case of Euler characteristic 0, but in this case, where you fix the appropriate dimension and you allow for torsion in the homology, versus the case of integral homology spheres, where it's much more rigid. Okay, so now we want to get to the topic of the title of the talk, which is really about even dimensional manifolds with a fundamental group G. So here I will consider manifolds of dimension divisible by 4. And the motivating question for this analysis, and the work here is joint work with Ian Hambleton also. So after we looked at the case of at 3, we wanted to consider the case of 4 and other even dimensional manifolds, and building on work that he and Matthias Craig had done on this in the 80s. So the motivating question here is, which finite groups can arise as fundamental groups of 4 manifolds M, which are homology spheres? So, and so in particular, this corresponds to the case when the Euler characteristic of M is equal to 2. So if Y is the universal cover then the Euler characteristic of Y is going to be equal to 2 times the order of the group. So let me just explain that again. So you're looking now downstairs and asking, what are the 4 manifolds, right? Which finite groups can appear as fundamental groups of 4 manifolds, which are homology spheres? So you're assuming then that the Euler characteristic is 2 there, and then you go upstairs to the universal cover. Now the universal cover will have a free action of G then. So the Euler characteristic upstairs is going to be 2 times the order of the group G. So, the question is, which finite groups can arise in this way? So there's a nice result due to Teichner from 1988, who says the following: a finite abelian group G is the fundamental group of a closed 4 manifold with a rational homology of a 4 sphere if and only if G can be minimally generated by 3 or fewer elements. So again, we're getting a group theoretic condition. We're going to do a little analysis of this, and again take an approach using group cohomology, representation theory, to shed some light on this type of question. And we'll also generalize an invariant due to an invariant for 4 manifolds due to Hausmann and Weinberger that it can be generalized to higher dimensional manifolds. So, so how do we do that? Well, first, let me recall. Let's call Q4 of G the minimal Euler characteristic of a closed-oriented 4 manifold such that its fundamental group is equal to G. And let's introduce some notation. Let H upper I of GF be simply the dimension of the cohomology of G with coefficients in F. Now, a basic result due to Hausmann and Weinberger. So this invariant was introduced by Hausmann and Weinberger, and in their theory, in their paper where they introduced it in '85, what they prove is the following: for any coefficient field F, H2 of G minus 2 times H1 of G plus 2 is less than or equal to this invariant Q4 of G, and this is less than or equal than 2 times 1 minus the deficiency of G. Here, the deficiency of G, it's a classical invariant for groups, is the maximum difference D minus R of numbers of generators minus relations over all finite presentations of the group G. So it's telling you then that this invariant relates to cohomology, and it also relates to the group theory, the presentation, this deficiency of the group. So how does this look in terms of higher dimensions? Well, first of all, if we take G equal to ZP to the K, then you can calculate these dimensions, and you obtain the following inequality. So again, thanks to the, we're doing this with coefficients in a field. For a P group, the only field that's going to matter is going to be P, and it's a simple computation using the Kunitz formula. So you have this nice bound here, like this, and the lower bound in Teichner's result follows from this very simple inequality. Now, more generally then, you say, well, how does this generalize to higher dimensional manifolds? So we define now Q4n of G to be equal to the minimal value of the Euler characteristic of M over all closed orientable 4n manifolds M with fundamental group G, such that the universal cover is 2n minus 1 connected. So what we want is the universal cover of M to be highly connected. And the point here is, so we're mimicking the situation for these 4 manifolds where we know, of course, the universal cover is going to be simply connected, and the first non-zero homology is going to be in degree 2. Here we want the first non-zero homology to be in degree 2n, in that middle dimension. And the point is here that you have, if you want to have control over these actions, this gives you a piece of the action which is governed by the theory of projective resolutions for the finite group G, as you shall see very soon. Let me see, how are we doing for time? Okay, 8:40. So let me see. All right, so now we generalize that. So now, what do we do? Well, we start plugging away at these numbers using group cohomology. So we define En of G to be the least integer greater than or equal to the following numbers. Well, you take all the primes dividing the order of the group. So here I'm focused entirely on finite groups, although some of the results here actually hold for more general types of groups. Again, refer you to the appropriate paper on the archive. So we're going to be taking Hn and then subtracting 2 times the alternating sum from Hn minus 1 all the way to H0. And here P ranges over all primes P, dividing the order of the group. And let me recall a definition due to Swan. We define mu n of G for every n greater than or equal to 1 by the condition that the order of the group times mu n of G is the minimal value over all partial Euler characteristics of a projective resolution of Z truncated after n steps. So you're taking a truncated projective resolution. You can do this just for free resolutions if you want, and then extend it to projective resolutions. For the purposes of my statements, I want to do this for projective resolutions. And then you have so you have a projective resolution, then you truncate it, and there's going to be a certain kernel over there. And we have this equation that relates the rank of this kernel. These are all torsion free, and this number. So that's how you determine mu n of G. And what we know from the classical work of Swan is that mu n of G can be computed using the cohomology of groups with coefficients. So now we're in the realm of where you have to compute, understand the cohomology with coefficients in every simple module. So that's where things get kind of interesting from the point of view of group cohomologists. Okay, so that's a number. So then the result then, which appears in our preprint with Ian, is the following. Suppose G is any finite group and n greater than or equal to 2, then this minimal Euler characteristic, Q for n of G, is greater than or equal to the maximum of E2n of G. So this takes care of all the sort of the group cohomology with trivial coefficients over the different finite fields characteristics that divide the order of the group. But then we have this number here, which has to do with the sort of deeper cohomological invariant in terms of the resolutions, and appears here over also. And so it's greater or equal to this maximum of E2n of G, comma, mu2n of G minus mu2n minus 1 of G, and it's less than or equal to 2 times mu2n of G. So how would you get that upper bound? Well, the upper bound, for that, you need to show that there exists an M with pi 1 of M equal to G, and with the Euler characteristic of M equal to 2 times mu2n of G. So it's a constructive approach. And the other one requires sort of a spectral sequence argument, and also an argument where you can break up, you can analyze the action on the universal cover and model it on projective resolutions and keep track of the ranks of these partial resolutions and how they the kind of input that they give when you write down the homology of the space. So it's sorry, an argument in homological algebra, but it requires a little bit of representation here. And now this improves and generalizes the result of Hausmann and Weinberger. And for example, just to amuse yourself, if this amuses you, if you have a ZP to the K, then you have an inequality. It's a 4th order polynomial less than or equal to Q8 of EK. So you see here that Q8 of EK is greater or equal to 3 if K is greater or equal to 3. So there is no homology 8 sphere with pi 1 of M equal to EK for K greater or equal to 3. for example. So it gives you interesting kind of invariance. And these, of course, these numbers are not hard to compute once you get the group cohomology machine working. Now, of course, the most interesting results are going to be for groups that are not abelian, groups that are complicated, that have complicated cohomology, and which are not easy to compute. So if we take the alternating group A4 or A5, either one of those alternating groups, then you can compute these invariants. E2 of G is equal to 3, U2 of G is equal to 2. So you get the inequality that Q4 of G is sandwiched between 3 and 4. But in fact, you can show that Q4 of G is equal to 4. You can actually prove that explicitly. Now, Swan showed that in fact, mu2 of G sits between 1 and 1 minus the deficiency of G. Hence, if G is a group of deficiency 0, then mu2 of G is equal to 1. And for such groups, we can construct a rational homology force sphere with pi1 of m equal to G. So that goes back to the original kind of motivating question. Now, of course, the minimal possible value of Q4n of G is 2. And if achieved, will be realized by a homology 4n sphere. And this holds if mu2n of G is equal to 1. So for example, mu4 of A4 is equal to 1, Q8 of A4 is equal to 2, and there's a rational homology 8 sphere with fundamental group A4. So these are results you can get by looking at these bounds. Now, we were originally looking to find examples of groups that do not appear as fundamental groups, and we wanted to use certain twistings to do that. So here is one of the theorems that gives us examples which do not arise as fundamental groups. So let me explain what we mean here by this notation. So you take P a naught prime, and EK we know is ZP to the K, a product of K copies of Z mod P. And then C is going to be a cyclic of order prime to P, acting on each ZP factor. Here Q is a unit in Z mod P, so you take that semi-direct product. And you have conditions. So if this does not give you x to the q is different from x for all non-zero x in EK, then for all k greater than 4, UK, which is the semi-direct product, does not arise as the fundamental group of any rational homology force. So this gives you an example that different from the ones you saw before. And if q is equal to p minus 1, then for all k greater than 1, UK does not arise as the fundamental group of any rational homology force. So, the proof of this requires using modular character theory and cohomology to compute mu2 of G. So, and the point here is that this is something which is not would not arise from just using trivial coefficients. You really have to use the twisting. So, this is a sort of an example of the kind of results you can get from this analysis. There's a more this can be generalized to other groups. We have some results for more general discrete groups with some conditions on their homology, on their the types of resolutions that they allow. But for the purposes of this talk, it's best I'll just leave it at these finite groups. So just to summarize then, you see that the problem of trying to understand the finite groups that act freely on a particular manifold or that arise as fundamental groups of manifolds with certain homology really involves a very intricate combination of well, geometry, homotopy theory, representation theory, and group cohomology, which of course is the kind of technology that is my favorite technology. Of course, that's a professional bias. So maybe this is a good place to stop. Thank you.
Thank you very much, Alex. Thank you very much for a great talk. All right, we have a few minutes for people asking questions or comments? Alex, I would be curious about what are the future directions of this theory? What techniques and kind of problems that you would, besides the one that you already mentioned, other problems that you would be interested in solving, and new techniques probably?
Yes, I think you have to really understand actions and the homology representations, how the twisting in the homology representations can be all brought to bear as restrictions on the action. And if you see every result that we have, or where we get away with something very special about what's happening in the homology, either it's in one dimension or it's nothing is happening, and those are the ones which restrict. So how do you deal with that in a more general and systematic form as flowing into the theory and how they interact between them, right? And the other aspect, of course, is trying to understand what I said at the beginning about, in the work with Jeff Smith, the key thing was to consider arbitrary spaces with periodic homology. So now you would want to talk about arbitrary spaces that have this, what we call the Cohen-Macaulay property, free and finitely generated over polynomial subalgebra. And the general conjecture would be that these spaces should sit as the base of a fibration with spheres, a product of spheres as the fiber, for example. This is like the topological way of realizing this thing which has n essential generators as a polynomial type algebra. This is like the fundamental kind of principle underneath it, but proving something like that is very difficult because when you use spectral sequences, things get out of control. So I think a more comprehensive approach to that would be very interesting. I think we need to use a lot more homological algebra and understand much more. There's been a lot of progress in the techniques from commutative algebra and so forth, and I'm hopeful some of that can be used. Of course, also representation.
And what about the non-free actions? That might actually be closer to applications from physics or something like that. And what are the techniques in general?
Indeed, yeah. Well, there, of course, the orbifold techniques apply there, and I think the situation is that you need to have maybe some geometrically or physically interesting class of actions, where certain actions arising from, for example, string theory in dimension 6, the toroidal orbifolds. And that gives it's a very nice theory, a nice classification, and you can do some very interesting computations there. Then you're reduced to doing some calculations, for example, in equivariant cohomology, and it connects with some gerbs associated to the orbifold. And again, there's some very interesting questions there, and certain situations where spectral sequence does collapse, and others where it doesn't. So again, I think you get a gradual understanding of the situation, but as we know, with groups and anything which involves groups and their actions, you need to have some geometric, precise understanding and knowledge about the situation you're working on if you want to prove something that goes beyond the generic. So that's what I guess what this tells us. You really have to know a lot about the groups, about their cohomology and their representation theory, and how all that fits together.
Thank you very much. Any other comments? Well, if not, let me thank Alex. Thank you very much for your participation in this celebration activity. So I'm going to be stopping now the recording.